We continue from where we stopped. We are still exploring case 1, absence of a catalyst. So I take another example where we have propanone reacting with Brady's reagent. Hope you still recall what I mean by Brady's reagent. If there are things which you are supposed to forget, Brady's reagent shouldn't be one of them as far as carbonyl compounds are concerned. I have said, under carbonyl compounds, if there are things which you are supposed to forget, let Brady's reagent not be amongst those things which you are supposed to forget. Yeah, you should prioritize it amongst all the other things, physical properties, nomenclature, because it is very common also in practicals. It's used to confirm for the presence of carbonyl functional group, as we shall see with time to come. So still, it is a derivative of ammonia. And don't forget from the previous video, I have stressed this a lot, NH2. NH2 is used. I have also stressed this a lot. The reaction mechanism does not change. I have said that exhaustively. I'm even tired of saying it. So what do we have? We have expose the functional group, CH3, see, like that. So after exposing the functional group, the carbon to oxygen double bond is polar because oxygen is more electronegative than the carbon. So oxygen takes carbon, becomes electron deficient. So you bring your derivative of ammonia. In this case, my derivative of ammonia is a bit complex, however manageable. This is how it looks like. A bit complex, but easily manageable, can be handled with ease. This is how it looks like that. Now, we use lone pairs of electrons on nitrogen. This nitrogen that has 2 hydrogens, we cannot, note that if you use lone pairs of electrons on this nitrogen in red, if you use lone pairs of electrons on that nitrogen in red, you outline a wrong reaction mechanism. Electrons on that nitrogen in red are not readily available for protonation. They interact, if you recall, effect of substituent on a benzene ring on the rate of reaction from your discussions with your teachers. Effect of benzene, effect of substituent on benzene on the rate of reaction. The lone pairs of electrons on this nitrogen in red, they are not there. They are interacting with the localized electrons of benzene. They are not there. So if you use them, you'll be right, you'll be outlining a wrong mechanism. So they are not readily available. So you use those which are here. And you donate them to carbon. I don't know. My thing is a bit congested. Yeah, so you use lone pairs of electrons on that nitrogen, then donate them to carbon, which is electron deficient. Yeah, like that. So after that, what do we have? The chemistry doesn't change. It is the same chemistry. We have CH3. See, this is now a single bond with oxygen. And there is a negative. Carbon carries CH3. I am bonding it with carbon carries CH3. That oxygen has a negative charge. Maybe since this is a new video, I'll re-explain again. Oxygen has a negative charge. Why? Because one bond has been broken. So that negative corresponds to one of the bonds which were originally present. Yeah. So we have excess electrons there. So this carbon, I'm bonding it with N. N has a plus. Carries 2 hydrogens where I expose 1 hydrogen. Yeah. Like that. Then that N also has NH. So it has another N that carries hydrogen, and also this N has a benzene ring. Yeah. So long as you represent it correctly. Yeah, you may not mind about how, so long as it is attached there, the bonds are done appropriately, yeah, there's nothing so much to worry. So nothing so much to worry about. So that's what I have. So this nitrogen is electron deficient. I give it electrons using the hydrogen appending from it adjacent hydrogen like that. Now, once I give it electrons, that is a covalent bond. And I am taking electrons from that covalent bond, giving them to nitrogen. Remember, hydrogen contributed electrons towards formation of that covalent bond, and electrons are picked them from that bond, donated all of them nitrogen, meaning hydrogen is electron deficient. Therefore, it has to look for where we have electrons. It has to go to that oxygen up because it is the one which is having excess electrons. As a result, what do we have? We have hydrogen shift. Hydrogen shifting to where we have excess electrons. As a result, so that we form CH3, C with another CH3. I'm having OH like that. Also, this carbon is bonding with N. Like that, it is bonding with N which has H, bonding with another N with H. That N has benzene ring. With NO2 and another. Now, what is this? Hope I am there. What is this thing? Wants to destroy. Yeah. So we have a 2 here on the NO2. And the hour bonds, don't forget to attach them like that. So still here, I have a polar bond between carbon and oxygen. Oxygen is more electronegative, oxygen is more electronegative, so it takes, carbon becomes electron deficient. There are lone pairs of electrons on nitrogen. I donate them, that carbon. So what have I lost? I have lost hydroxide ion. I've lost hydroxide ion as I form this board is going to let me down because I think I have to reduce on the material. It's a bit slow. So I form a CH3 with C, CH3. This is now a double bond with the N that has a plus because it has donated. That N carries hydrogen like that. Then it also carries another N. And by the way, this another N has hydrogen. I am also bonding it with the benzene ring. This. So nitrogen is electron deficient. I give it electrons like that, using the hydrogen adjacent. So as a result, I lose the proton minus hydrogen ion as I form CH3, C, CH3, double bond with N. There's also another N which carries hydrogen, and this N carries the benzene ring like that at position 2. also at position 4. Then the hydrogen ion plus hydroxide ion, we get a water molecule. And the compound which we have formed is the hydrazone. Why? Now what is this thing? Yeah, that's disappeared. So what do I have? I complete my reaction mechanism. My equation, I have formed CH3, CH3, double bond with the N, H, benzene ring here. Two, and that 4. Like that, plus H2O. Now that is done. So I think I've done enough. I've done enough for this one, isn't it? Maybe if it is not enough, you comment in the chat. You comment in the chat. But I think I've done enough. Maybe okay. One more example. Maybe. So what is the name? The name is. It has been formed from 2,4-dinitrophenyl hydrazine, 2,4-dinitrophenyl hydrazine, and propanone. So if we have hydrazine, we form hydrazone. So the name is, the name of the product, maybe I put it here down. The name of the product is propanone. Propanone 2,4-dinitrophenyl hydrazone. That is the name. So I take another example. I hope that is taken note of carefully. Involving Brady's reagent, I have said you should recall this. If there is anything which you have to forget under carbonyl compounds, let it not be Brady's reagent. So another example, I take which one? Previously, I've been doing the benzaldehyde. Which other interesting example? Another interesting example, which I can think about, phenylethanol. Still with Brady's reagent. You know, you people may think that these things are difficult. Yeah, but they are not. You just have to give them some time. And the Brady's reagent. That one. So I outlined the mechanism. The chemistry doesn't change. The chemistry is the same. Expose the functional group. Those are the basics. Expose the functional group. So I expose my functional group very well. Carbon to oxygen double bond is the functional group. So you expose it distinctively. And we have said severally, I think I don't need to repeat this. We have said severally that this bond is polar. So oxygen takes carbon, becomes electron deficient. Now you bring the derivative of ammonia, and I have been saying severally that this derivative of ammonia is electron rich. Don't forget that the derivative of ammonia is electron rich. Why? Within it we have nitrogen that has lone pairs of electrons. I have been stressing this also severally, that we use NH2. We get lone pairs of electrons from NH2. Yeah, from NH2. Now here, I have emphasized from the previous example. There are two nitrogens here. There is this nitrogen in red. There's that nitrogen in red. Then there is also this nitrogen in black. Okay, maybe in pink. You see, those nitrogens are not the same. Don't take lone pairs of electrons from this nitrogen in red because they are not there. From your discussions with your instructors on effect of benzene reactivity, on effect of substituent on effect of substituent on the benzene ring on the rate of reaction, your instructors highlighted that those lone pairs of electrons, so long as you have that nitrogen bonded directly to benzene, the nitrogen bonded directly to benzene, the nitrogen bonded directly to benzene, I repeat, the nitrogen bonded directly to the benzene has no lone pairs of electrons. Why are they not there? They are interacting with the localized pi electrons of the benzene ring. So they are not there. You use lone pairs of electrons on this other nitrogen, then you donate to carbon. Let me pick up this call. Hello. Hello. Siriyo naye ngenda kubaayo mu ssaawa ng'emu. Soolo zireeta ssaawa nga 2:00 oba 2:40 awo we watyo. So what do we have here? We have our ketone, a bit complex, reasonably manageable. Yeah. So with the C, this is now a single bond. Oxygen has a negative. This carbon carries methyl group. That carbon, I am bonding it with a nitrogen that has donated, therefore has a plus, a nitrogen that carries a hydrogen, and another hydrogen, and another nitrogen, which nitrogen carries a hydrogen. Now that nitrogen, I am bonding it with benzene ring. I am not drawing it correctly. Carries a benzene ring. Like that. So that is what I have. Now in this compound, nitrogen is electron deficient. I give it electrons using the hydrogen appending form. That hydrogen also becomes electron deficient. We have seen this severally. So it becomes electron deficient. It looks for where we have excess electrons. It goes there. As a result, we have hydrogen shift. This space will be enough. We have hydrogen shift, the hydrogen going to where we have excess electrons. So we have our benzene ring, C, now with OH. That C carries CH3. That C carries N, which N has hydrogen and another N, which carries hydrogen, and this N carries a benzene ring. Yes. NO2. So that is what we have. Now in this compound, the carbon to oxygen bond is still polar. Oxygen takes, carbon becomes electron deficient. So we use lone pairs of electrons on nitrogen and donate to carbon. As a result, we have lost hydroxide ion. We have lost hydroxide ion as we form our benzene ring. From our benzene ring, our benzene ring with the carbon, with the CH3, with the double bond, nitrogen, which has plus, nitrogen carries hydrogen, nitrogen, then with another nitrogen. But down there we have a benzene ring. I think I have to attach that benzene ring. My screen has frozen. Okay, we are there. Nothing so much to worry about. So I am bonding this nitrogen with a benzene ring. Yeah, like that. So still here, we lose a proton as a way of giving electrons to nitrogen. So there is a loss of a hydrogen ion. Loss of a hydrogen ion as we form. I hope I've not forgotten. Yeah, there's nothing. As we form our product. So N H. This N as the benzene. That. Then the hydrogen ion plus hydroxide ion form H2O, like that. So what is my product? Always recall that you have to complete the given equation. Complete the given equation, most of you tend to forget that. So I complete my equation. The space is enough. Nothing so much. What about the space is more than enough? So I attach my product here. With NH. This N. Like that. Like that. plus H2O. So I want to give you some questions on that thing I've said. If there is anything which you have to forget, let it not be Bradley's reagent. So therefore, outline this mechanism, and this marks the end of case 1. Next time, I am not coming back with case 1. I am coming back with some other important things on case 1. So kindly, I have not named the product. Now you are experts of nomenclature. If you have worries in naming that product, reach out to me in the chat. So you complete that, then you also complete this. These are very easy things, so long as you give them time. This is cyclohexanone, still with the one which you shouldn't forget, Brady's reagent. Yes. So as of now, allow me stop here. So we shall continue with other important reactions next time.